And if we take the wave function as depending on a set of complex parameters lambda, we would have the variation, time evolution of the wave function expressed in terms of the time evolution of the parameters. And so we can define as the vectors, like these variation vectors living in the tangent space in terms of the derivatives of the wave function with respect to the parameter. So these are like a set of vectors that span the tangent space for a particular approximate form of the wave function defined in terms of these lambdas. This means that the projector onto the tangent space reads like this. So we project onto these delta psi vectors. And we have this so-called ground matrix and the C matrix, like the overlap of these vectors that actually defines a metric of the tangent space. And so with this projector, we can explicitly work out the projected Schrödinger equation, which is going to be formulated in terms of the time evolution of the parameters. So we simply take this explicit form of the projector that we just looked at, we insert this, and finally we get these equations for the parameters, where the C matrix or the ground matrix appears again, and we have this Y vector, which relates to the action of the Hamiltonian on the wave function. Now, this C matrix is a complex valued Hermitian matrix that comprise a real and imaginary part. The real part defines the metric of the tangent space, and the imaginary part defines the symplectic form. And if we actually have a set of complex parameters, then it turns out that we get norm and energy conservation, which actually results from this relation between gamma and omega. And we have symplectic evolution, and the mathematicians also refer to this as a Kähler manifold. Right, and this is the type of situation we often have in our numerical applications. One example is Gaussian wave packets. This is the general form for Gaussian wave packet, actually including the case where we have a time evolving width of the wave packet. And so here we have this A matrix, the width matrix, this complex symmetric. We have this psi vector, which describes a phase space point. The real part is the Q variable, coordinates average variable, and P is the momentum variable. So this is a Gaussian wave packet, and you get a coherent state if you simply fix the width matrix as time independent. Right, and we also have a complex phase, which includes the normalization as a real part and the classical action essentially as the imaginary part. So, right, so this is a typical ansatz for the wave function. In this case for a Gaussian, we use the Dirac-Frankel variational principle, and we get this equation. Now, if we look in detail at the result, we're going to see that we get a classical evolution for Q and P, so for the components of this psi vector, and we get the usual equations for the width and phase. And I should mention that this is a particular case where the complex parametrization can actually be formulated in terms of pairs of complementary real parameters, which is not always the case. And in fact, this parameter evolution for a Gaussian wave packet is a given in terms of Gaussian moments. And I think there is a connection to the previous talk by Martin Boyewald, who actually looked at these variational equations for moments. And if we ask, like, for the h bar to 0 limit of these Gaussian wave packets, then we contact the presentation by Caroline, who is actually looking in detail at the properties of the classical limit. Now, second example that we're going to use, a different type of ansatz for the wave function, which is suitable for many-body systems. We're going to take tensorized wave functions in many dimensions, and in particular, we are interested in multi-configurational wave functions. There are these complex value time-dependent coefficients here, and then there are these configurations phi, which are product configurations. So if we have just a single configuration, this is a simple Hartree method, time-dependent Hartree. And if we have multiple configurations, we have the multi-configuration time-dependent Hartree method, MCTDH, which is actually used quite a lot for high-dimensional quantum dynamics in our community. Actually, this is also related to so-called matrix product states that are more used in physics. Now, the idea here is that we have as variational parameters these coefficients, and then these time-dependent so-called single particle functions that live in the individual subspaces. And by using the Dirac-Frankel variational principle, we're going to get equations for these quantities. Now, just another way of looking at this. So MCTDH is also a low-rank tensor approximation scheme. In the sense that these time-dependent basis functions are going to be expressed in a time-independent so-called primitive basis. And if you write a wave function in this very general way, right, in terms of a time-independent primitive basis, you're going to have this coefficient vector here. And what we're actually doing is to approximate this coefficient vector in a particular way, actually using this A vector here. And so in the physics and math community, this is generally referred to as the core tensor. So it's a low rank approximation in the sense that these summations with respect to this time-dependent A coefficients and these U's, which are actually the transformation between the primitive basis and the time-dependent single particle basis. So this transformation is such that the summations here are much lower dimensional. So the number of basis functions in the time evolving picture are much lower than the original number of basis functions in the primitive representation. All right, so we have as variational quantities, these A coefficients and the time evolving single particle functions, and the variational principle is going to give effective equations of motion for the coefficients with these matrix elements of the Hamiltonian in the basis of full configurations, and this highly nonlinear equation for the single particle functions. Now these are multi-configurational mean field equations. So in the simplest single configurational limit, we just have time-dependent Hartree. So there is one mean field Hamiltonian, and here we have a matrix of mean field Hamiltonians. And also there is this projector here. Actually, this is different from the tangent space projector we mentioned before. This projector actually projects on the subspaces, the single particle functions in the subspaces, and it balances the part of the time evolution that is taken care of by the coefficients and by this nonlinear equation for the single particle functions. All right, this is essentially what we are working with, and these equations actually allow one to address a very large number of degrees of freedom. So like typically 100 modes or so, and a number of electronic states. Now, against that background, we actually started turning these wave functions into a hybrid form, quantum semiclassical hybrid wave functions, by saying that we can use configurations that are partially composed of these SPFs, single particle functions from the multi-configuration time-dependent Hartree approach. And then there are part of the configurations that are actually expressed in terms of Gaussians, because we want to have this hybrid picture expressed here in terms of coupled primary and secondary modes. So the primary modes are kind of the full quantum subsystem that needs to be treated by MCTDH-like equations. But the secondary modes are supposed to be simpler, and they're expressed by these Gaussian wave packets. And of course, we have the second thought now that at some point we want to turn these Gaussians into classical-like quantities. Right. So now we have these hybrid configurations, and these include these Gaussian wave packets that look just like the Gaussian wave packets we introduced previously, written here in the most general form, so including a time-dependent width matrix. But again, so if you keep the width matrix fixed, then we just have the motion of this psi parameter, which includes the Q and P parameters defining a classical phase space point. And one advantage is actually that we can do all the integrals analytically. So everything is going to be expressed in terms of Gaussian moments for the subspaces where we actually use these G functions. All right, now we use this ansatz for the wave function in the Dirac-Frankel variational principle, and we are going to get equations for these A coefficients for the single particle functions that still look like in the original MCTDH method, and then for these Gaussians here. And that's what it looks like. So the first two equations for the coefficients and the single particle functions for the primary modes are very much like in the original method. But then we also have now the equations of motion in the secondary subspace defined by these Gaussians. And this equation is what we discussed before. It is what you'd get in general from the variational principle for parameterized wave functions. And since these Gaussians are non-orthogonal, and we're going to have actually many Gaussian wave packets, so we have superpositions of Gaussians in this multi-configurational context, so we will have overlap matrix elements between all these Gaussians, actually different sorts of overlap matrix elements involving these differentials and so on. So this is the explicit form of this C matrix, the Gram matrix, and this Y vector. Now it turns out that we get these coupled equations between multiple Gaussians, and these turn out pretty non-classical. It's like in the zeroth order description, we would have like one Gaussian with classical time evolution, but here we have many coupled Gaussians, and in fact the dynamics may look pretty chaotic, so highly nonlinear, and these Gaussian basis functions are coupled among each other. Okay, the classical evolution follows as a special case. So first, if we have just a single Gaussian wave packet, we know that we get classical motion of the phase space points defined in terms of Q and P. And there is also a special case where we have superpositions of third Gaussian, so those with a flexible width matrix. Then we also get simple classical equations of motion. Now, we also expect to get classical equations if the classical limit is actually reached in the sense of Caroline's presentation. Or if you think of the condition that the de Broglie wavelength is much smaller than the scale of variation of your potential. And then this Gaussian-based MCTDH would actually become a true mixed quantum classical method. And that is what we actually want to look at in the next part, which gives some details of this quantum classical limit. Now, we are thinking again in terms of this picture, in terms of primary and secondary modes. And the difference with respect to the previous approach is that we now want to take these Gaussian wave packets and we bring them to a classical type limit in the sense of Caroline's presentation. Now, in a sense, we remain in this wave packet picture, right? So, we never go to a pure classical trajectory picture here, but rather we have these epsilon scaled Gaussians that are characterized by a classical-like dynamics. So essentially we're thinking of these narrow semi-classical wave packets. And this is exactly the epsilon to zero limit that Caroline referred to. Or put in a slightly different way, we can think in terms of this, this typical WKB type a condition on the scale of variation of the potential. And the scaling operation that was described by Caroline can also be thought of in terms of the scaling of the potential. And we get to sort of macroscopic coordinates in terms of which the time-dependent Schrödinger equation reads like this with this epsilon variable that here is essentially replaces h bar. Okay, so this is like the limiting process we have in mind. And this means that the Gaussian wave packets essentially become narrow, both in coordinate and in momentum. So these are actually results that have been obtained by Hagedorn and others quite a while ago. So, so essentially we contract in Q and in P, and this also means that the uncertainty area is contracted. So kind of we move towards a phase space point. And this would mean that like the semi-classically scaled Gaussian wave packets move along classical trajectories, and the phase is given in terms of the classical action, and one can do various explicit estimates. There is recent work also by Caroline for Gaussian wave packets in this frozen or thawed form, so with or without time evolving with matrix, and she can quantify the approximation error that is done as a function of epsilon. And also for this multi-configurational dynamics, we actually see that in this epsilon to 0 limit, the Gaussian wave packets become decoupled from each other because they lose their overlap. Yeah. And this now means for our complicated looking equations that were discussed before, that we have a significant simplification in the secondary subspace. So the quantum subspace kind of remains as before, but in the secondary subspace, we now see that the equations can be simplified to classical equations of motion because we lose the coupling between these Gaussians. That was actually generated by the variational treatment. And the result is something like a multi-configurational Ehrenfest type approach. So Ehrenfest because we keep this mean field picture, and multi-configurational because we keep a wave function that is sum over products, but in these configurations we now have the classical-like part in this secondary sector. And these are these epsilon scaled G's. And right, so let's look at this for the very simple example for a two-level system in the quantum subspace. And this would mean that we have like this quantum classical wave function. It's like with this epsilon scale coherent state, and we get these equations, which you will actually recognize as simply the Ehrenfest equations. And the point is that like behind these equations, we still have like this multi-configurational form of the wave function. So we have this superposition of Ehrenfest trajectories. So here again for illustration, so the Ehrenfest picture as such would mean that we have like a classical, like a particle moving on an average potential. And in the multi-configurational Ehrenfest approach, it's essentially that picture, but it's kind of not statistical. It's not just like adding up multiple standard Ehrenfest trajectories, but we still have this underlying multi-configurational wave function form. Now, I will show an example, which is actually not fully in this quantum classical limit, but we use these superpositions of Ehrenfest configurations, but we are doing so numerically for finite width Gaussian wave packets. This also means that the equations will be modified a little bit because we have to take care of the fact that we sort of go a step back. We are actually using these finite size Gaussians, and we have to take care of the normalization and so on. And if we do this, you get this type of picture for a spin boson type model. I'm going to say more about this system in the third part. So here, just take this as a spin boson model. So we have a two-level system in the quantum part, and then we have a variable number of modes in the part that is kind of becoming classical. And n equals 10, 20, 40 means that these are the explicit numbers of modes, vibrational modes that are treated in the spin boson Hamiltonian. Right, this is an example where Ehrenfest is doing very badly. The dashed lines are the Ehrenfest approximation. The populations are pretty bad. And the reason is that actually the electronic coherence cannot be represented correctly. And we see that when we use this multi-configurational Ehrenfest approach, we actually get to the exact dynamics. So black is the exact dynamics with the multi-configuration time-dependent Hartree. And so blue and red are two realizations which involve different sampling schemes. First, a Wigner type sampling, second, an improved sampling. That actually means that we use a compression scheme for the initial Gaussian wave packets. And you see that we actually approximate the exact dynamics quite well. You also see that with a larger number of degrees of freedom, one of the approximations, the one with the Wigner sampling, actually gets worse and approaches Ehrenfest. The reason is that we actually lose the overlap between the Gaussians, and that depends on the sampling. Now, the key is that we get the coherence right. And so in fact, the coherence in the system would be described in terms of a reduced density matrix of the quantum subsystem, which is actually in a mixed state in this multi-configurational formula. If we just have Ehrenfest with a single configuration, the subsystem is always in a pure state. So here it is in a mixed state. You can construct this for a general quantum classical wave function of this type. And clearly, the off-diagonal elements which relate to the coherence depend on the overlap of these Gaussians. And so that's what the overlap looks like in our kind of epsilon scaled approximation. And we see that we have the difference of classical actions here entering the phase. And so it's of crucial importance to see whether this overlap gets lost completely or not. And it turns out that in the example we looked at, actually of the time scale we are looking at, this overlap is important. So put in terms of the simple picture, we have the quantum subsystem here. And if we completely lose the overlap between these Gaussian wave packets, this really means that in the end we go to something like a statistical Ehrenfest limit. But as long as the overlap is non-zero, we actually have this influence of the multiple configurations on the coherence of the subsystem. And typically in the molecular systems we are looking at, we see very fast decoherence, but it's visible on the time scales we are looking at. So actually very often like femtoseconds or picoseconds, so very fast time scales, but the coherent effects are important on these time scales. So from these semi-classical scaled wave packets, we can expect that we initially do keep some coherence, and then we can actually quantify the decoherence effect that we see. So question, is this multi-configuration Ehrenfest dynamics consistent? So with the properties of the underlying wave function state are preserved. In the end, we keep this wave packet picture. We don't go to a strict trajectory picture. We will say that these narrow coherent states are as far as we can go in terms of a kind of consistent quantum classical approximation. Correlations are accounted for between the quantum and classical subspaces, and the dynamics is variational from the Dirac-Frankel variational principle, and therefore we have a general Poisson bracket structure, and in that sense the dynamics is going to be consistent. Now one should remark that the single configurational standard Ehrenfest case upon which we build is not a satisfactory quantum classical description as such, because correlations are not encountered. But so we construct these multi-configurational wave functions in order to get quantum classical correlations correctly into the picture. Now, due to the nonlinear structure of the equations, a direct comparison with other approaches, for example, the quantum classical Liouville equation or Koopman wave functions, is probably not straightforward. So in the end, these are effective equations that we get from the variational principle. Now, if I still have some time, I hope that 5 minutes, 10 minutes are left.
Yes.
Great.
15 actually, so yeah.
Yeah. Excellent.
With questions.
I was going to yes. Okay. Great. So anyway, I'm very happy to go to this numerical part. This will probably help to see our mindset, like what kind of simulations are we doing standard wise, and how do we think in terms of this quantum classical approximation. The examples refer to system bath type dynamics, and I will give actually two applications. So one to diatomic molecule in a rare gas matrix environment. That's the picture I showed at the beginning. And then the spin boson type system that we just talked about in the multi-configuration Ehrenfest context. Right, so this is the first example. We have an iodine molecule in this rare gas environment. And we want to capture this dynamics. And for this, the system, we actually do calculations for up to typically 20 degrees of freedom, so vibrational modes. And we are doing this with a correlated Gaussian-based MCTDH. So this is not like the strict classical limit formulation. This is just MCTDH, including Gaussian wave functions. So we have like standard single particle functions for the quantum subsystem and Gaussian functions for the environment. And we have a limited set of most relevant modes of the environment, which we actually get from classical molecular dynamics simulations. And these are like collective modes of this cluster type environment with respect to the diatomic molecule. For example, like a cage breathing mode, etc. And these modes are included in the simulations. And one of our aims is actually to calculate spectroscopic properties. For example, pump probe type spectra, where we have like sequences of ultra-fast laser pulses. And we want to get, for example, these typical signals, which are highly oscillatory. This is experiment, actually. And so the oscillations signal that we have a persistent oscillatory motion of the diatomic molecule in this experiment on a time scale of 3 picoseconds, so 3,000 femtoseconds. And interestingly, in the system, actually dissipation is very fast. We have extensive dissipation within 400 femtoseconds, and decoherence is slower. So we actually get this wave packet motion out to much longer times. And these are our simulations, so done for about 20 of these environment modes, together with the quantum subsystem, which in this case is actually complicated. So we have this main electronic state, which actually has non-adiabatic curve crossings with various other states. So this requires a full quantum treatment, and so we have the MCTDH type treatment for the iodine molecule, and then the Gaussian treatment for the environment. These are some of the results, and you see that these results show these oscillatory features very much like the experiment. And so we actually compute third order polarizations here to directly model the experiment. We also looked at experiments where a molecular cat state is produced. These are Raman type experiments where we have multiple pulses. And so this cat state is a coherent superposition, and we get signals that directly inform about the decoherence in the system. So that experiment, it's a Raman type experiment where we have these anti-stake signals, actually directly shows a so-called coherence matrix, which is got from the experiment. And we see this decay of coherence on a time scale of about 3 picoseconds. Now, the second example I wanted to show is this spin boson system that we refer to. It's actually an idealized model for a real system where we have electron transfer or exciton dissociation in this system, which is relevant for organic photovoltaics. And essentially, it's a two-level system with a structured spectral density. And we actually get detailed molecular information on what the spectral density looks like. Now, this is an experiment for this type of system. We see an oscillatory decay, again, on a very fast time scale. And we get this in our simulations. These are actually simulations which were done in both with these Gaussian wave packets. So this is G-MCTDH, and with the original MCTDH method, you see no difference here actually at all. So the Gaussian base scheme is very precise. ML actually stands for multi-layer. I'll say something about that in a second. This is the spectral density again, and the motion of the modes that are represented by the spectral density. So we represent the environment here explicitly in terms of 300 modes, and we see that there is a very different participation of the modes and the dynamics depending on the frequency and the spectral density. Now, I mentioned that we use these multi-layer schemes. So actually there's a lot of sophistication in the construction of these approximated wave functions. So to go to a large number of degrees of freedom, we actually re-express these configurations in terms of single particle functions, but the single particle functions are in turn expressed in terms of sums of a configuration. So in this case, sums of a Gaussian type configurations. So we generate actually these trees, these hierarchical trees that the mathematicians actually call a hierarchical Tucker format. And these are the equations of motion. So you recognize the ingredients that we looked at before. It's just that we now have these two layers here. And here is again the type of equation we have for the variational parameters. And finally, the wave functions we use comprise multiple layers and a very large number of configurations. So you see that we easily get whatever, 1 million configurations or so. Yeah? And this is what we actually need to do numerically in order to converge. So in other words, what we're going to do in real life is to have kind of the superpositions of very many of these single particle functions and Gaussian wave packets. And this is a calculation sort of at the quantum level in the sense that we have fully variationally coupled Gaussian wave packets. And we will be very interested to see what this gives if we move to this partially classical representation. And the simulations I showed you before are sort of first steps in that direction. Yeah, so that was actually with this multi-configurational Ehrenfest type scheme where we have taken a number of modes, small number of modes to the classical limit. So to summarize, we have these multi-configurational hybrid methods like the Gaussian-based multi-configuration, time-dependent Hartree that are as such powerful numerical methods for high-dimensional molecular quantum dynamics. And these methods actually have a natural quantum classical limit in terms of this epsilon to 0 limit described by Caroline, which gives something like a multi-configurational Ehrenfest type approach. And we think that this is a consistent quantum classical or quantum semi-classical, depending on which semantics you prefer, scheme within a variational framework. Importantly, we keep an underlying wave function representation for the full system with these scaled coherent state objects, yeah, kind of whose uncertainty area within the phase space is contracted in that limiting operation. Okay, so these wave functions can actually be made exact. So there are mathematical investigations showing that these multi-configurational wave functions do approach the exact dynamics. Also, we have new tools that improve on the variational convergence, which can be quantified in terms of a local and time error. Yeah? And as a final remark, we actually prefer to use wave functions in this description because a corresponding variational description for densities is sort of a topic apart. This has certain issues. So if you transport the Dirac-Frankel variational principle to a density matrix, density operator setting, you actually naturally would use this Hilbert-Schmidt norm. Now this entails that actually energy conservation is no longer there. So instead you have a conserved quantity, which is like the trace over rho square times the Liouvillean. Yeah, so that this actually depends on the notion of distance, going back to this tangent space picture. Yeah. So the way you would define a distance with respect to density matrices to start with is not the same as the wave function procedure. This is actually why in applications we prefer like an expression of density operators in terms of wave functions, and we look at the variational evolution of the component wave functions. So a number of acknowledgements, people from our group in Frankfurt, so in particular, Sarah Römer and Matteo Banfanti. And then we have a collaboration with the mathematicians, so Caroline and her colleagues. And so thanks to everybody in participating in this, and thank you very much for your attention.
Thank you very much, Irene. And so now I can take questions. So please raise your hand or just start talking if you want to ask something. And if people are too shy, I have a couple of questions to ask you. So just to break the ice. So this is something. Oh, okay. I ask my questions and then I pass it to you, to the people who raised their hands. So at the beginning, you mentioned some singularity problems on the inversion of the density matrix. So in the initial slides, you have some rho to the power -1 in the equations of motion for the single particle functions. Yes. So I was wondering, how do you deal with the singularities?
Yes, actually, so these equations conform to that version of the variational principle. Yeah, and there is this issue about energy conservation, right? So for that reason, we did not pursue this, and actually we are now using a different approach, which actually expresses density operators in terms of pure state components. Yeah. And then you have a freedom to use a wave function based representation. Now there are different ways of doing this, different approaches, but in our context, actually the conservation properties are pretty important. So that is why we prefer to go back to the wave function level.
Okay.
It's an interesting topic as such, and there are different ways to go. And the underlying issue is really about this tangent space picture, yeah, and how this is modified when you go from wave functions to density operators.
Okay, so Jonathan, please go ahead.
Yeah, thanks for a nice talk. So I think this is a very naive question, just because I think there's a bit of a language gap that where I fail to understand some of the things. So it's a naive question, but I'm just wondering what the semiclassical when you're doing mean fields and when you're not. So like when I hear an Ehrenfest type approach or a Hartree approach, is it then that I can assume you're doing? Are you doing mean field then? Are you doing mean field the whole way through?
Yes, I'm not entirely sure whether I got the question better. So when we get to like these equations, now these Ehrenfest type equations, these appear in this limiting case, like in this epsilon to 0 case. So so if you actually go strictly to that limit, one would actually reach a trajectory type representation. Yeah, but actually, so this has to be investigated in a very clean way from the mathematical side. And when we operate with this and with the numerics, we are certainly not in this limit yet. That is, we are actually working with like a coherent state wave packet, yeah, that is still a quantum object, and we still have mean field equations in the sense of this quantum object. But in that limiting case, I mean, we would actually say that, like in the standard Ehrenfest approach, we would kind of define a trajectory, QP, and this actually determines the potential that is seen by the quantum subsystem.
Okay, and maybe this relates to, maybe another way of getting at it is, because I'm not sure I completely understand, but maybe a way of getting at it is to talk about energy conservation, because I guess one normally wouldn't expect energy conservation when you take the whatever you mean by the semi-classical limit, because your classical system is interacting with a heat bath or something like this. So you don't normally expect energy conservation. So is it that energy is conserved on expectation? Is that how I should think of it? Or
this
or that energy is conserved because there's not the full back reaction on the classical system, or what's going on?
That's a very good point, and it's actually currently under investigation. So the rigorous approach is kind of to take this tangent space projection and analyze what exactly is happening in this limiting case. This is one of the things that Caroline is currently starting to look at. And so our picture is that if one takes this variational procedure in a consistent way towards this epsilon limit, the conservation properties should be there. Now, from the numerical point of view, we're actually using this right now in a limit where we still have narrow Gaussians, right? So we do have the conservation properties. So I cannot give a rigorous answer yet. What happens in the full limit? But we expect that, due to the fact that we have the underlying variational principle, and we sort of gradually take this tangent space construction through to the classical limit, we get something that we can analyze in a clear way. But so as I said, numerically, we certainly have energy and non-conservation in the cases that we analyzed so far.
Thanks.
So next question, Stefan.
Yeah, thank you. You mentioned different tensor formats, for example, the matrix product state format or the Tucker format. And then the approximation typically depends strongly on the rank of these tensors. How do you choose these ranks? Do you have to fix them in advance, or can you choose them somehow adaptively? How do you do this in practice?
Yeah, so this is of course a good point. So maybe I just give this this picture, which is one of these typical hierarchical tree constructions, and it would be kind of similar for matrix product states, which actually have a somewhat different scheme to construct these hierarchies. So in general, we adapt the form of this construction to the physical system. So in this particular case, we have like the structured spectral density, and that determines to some extent which modes are grouped together. And very often we actually look at spin type chains or lattice models, which by their structure and by the fact that we have like nearest neighbor couplings, for example, essentially are strongly suggestive of the form that these hierarchical structures should take. But it's absolutely true that especially if we take a subset of modes to a classical limit, this partitioning is becoming more critical. Obviously. And we have the quantum classical coupling. So this means that we have correlations, which are encoded in general a very large number of configurations that interact. So I completely agree that the partitioning is a critical issue. Now, often it is obvious in the sense that, like in this spin boson model, we simply put the two-level system into the quantum part, and all the remaining modes are treated classical. So here, for example, kind of all these modes in the lowest layer are Gaussians, which represent our vibrational modes. Or for example, in a lattice system, we would also take like the lattice variables, raising and lowering operator or whatever, is the kind of defining the quantum subsystem, and the kind of the phonon modes would represent the classical part. But it is not always as uniquely defined as that.
Thank you.
So last question from Dimitri, please go ahead.
Thank you for a very nice talk. My question is about actual, maybe more technical calculations of dynamics. So at each time step, you have to solve huge system of linear equations. And in general, this huge system is ill-conditioned. So how do you fight with it? So do you use any type of regularization? Just kind of what mathematical tricks do you use to keep this solution physical?
Yeah, this is a very good question, of course. So let me just show these equations again. Okay, Yes, I mean, these are complicated nonlinear equations. Even if we do not have like these non-orthogonal Gaussian functions, even then it is complicated. So I should have added more explicitly that these single particle functions can be made to be orthogonal due to the gauge freedom that we have in this ansatz for the wave functions. This is an advantage, but still, you see, we have the inverse of the single particle matrix here. And for example, the initial condition is in general highly singular. So, so we certainly have to regularize. So this is done by standard schemes, and in general it works, but the regularization that we also need in this part for the coherent state type subset. So this is kind of less harmless, right? So we actually need to regularize inverses of overlap matrices and so on. Plus we run into linear dependencies. And so it turns out that in the case where we are kind of still, quantum in the sense that we have multiple Gaussian particles that are coupled to each other, we see that the evolution is kind of chaotic. It's actually a very irregular evolution, and we see these linear dependencies. We have not fully solved the problem, but we use some regularization strategies which actually bring us to the point where the dynamics is stable. Now, another important thing is that we have these multi-configurational mean field Hamiltonian matrices that we have to rebuild at every time step. Now, this actually works pretty well if you adapt an integrator to this situation. So we use an integration scheme which actually keeps the mean fields constant over a longer time interval. That converges very well. So-called constant mean field integrator that brings a huge acceleration. And it's used in the standard multi-configuration time-dependent Hartree equations and also in the extended version here. But so overall, you're absolutely right. The equations are stiff. Yeah? It is not trivial to solve these equations, but so the current status is that we can deal with this. But there are cases like of linear dependencies where we do not have a numerically optimal solution. Thank you.